So last time we introduced the equipartition theorem, which I didn't prove, but we're going to make use of, that every term in the total energy of a system that's proportional to an independent position squared or a velocity squared, and angular velocity counts as a kind of velocity, has on average a half kBt of energy if the spacing between the quantum levels is much less than kBt. And we're going to continue to explore this today. We use that together with our results from the kinetic theory of gases to derive the ideal gas law, PV equals N kBt, where N is the number of molecules. That's the physicist version, or nRT, where little n is the number of moles. That's the chemist version. We talked very briefly about the structure of an atom, emphasizing the point that the nucleus, which contains almost all the mass, is about 10,000 times smaller than the atom as a whole. And then we started talking about diatomic molecules, and we were writing down the total energy of them. So there's 3 terms from translation of the center of mass, 2 terms from vibration. There's a potential energy term here and a kinetic energy term, and then 3 terms associated with rotation. And then we made an argument that the moment of inertia for rotations about the z-axis, the axis that goes through the 2 atoms, is much, much less than the moment of inertia for the other 2 axes. So any questions about any of this?
Why did you write that the reduced mass is m? Isn't there a different version for that?
You're right, that's a typo. So I don't care that much that you know the formula for the reduced mass, just if you remember that it involves the masses of the 2 atoms. That's all that's important for our class. Other questions? Okay, so let's talk a little bit more about rotations about the z-axis and the spacing between quantum energy levels for rotation. So this is something that might surprise you, but in fact, objects are not allowed to just rotate at whatever speed they want to. The rotational speeds are actually, that are allowed by quantum mechanics, are actually quantized. For macroscopic objects, that is essentially never observable. But when you're talking about atomic scale objects, that quantization of the rotation becomes quite important. So again, I'm not going to prove every aspect of it to you, but I will start by just stating that quantum mechanics shows, and it's not that hard even in quantum mechanics to show this. So this is something that you will learn in PChem, or if you take introductory quantum mechanics, you can learn this, that angular momentum is quantized in units of h bar. Angular momentum is quantized in units of this constant h bar. So you write it as an h with a bar that you draw diagonally through the vertical part of it, where h bar is 1.055 times 10 to the minus 34 joule seconds, and this is called Planck's constant. Planck's constant. So when I say that it is quantized, if we think about, let's say, the rotations of a diatomic molecule, it is possible in that case for, if I plot, let's plot the angular momentum for rotations about the x-axis, it's possible for that to have a value of 0. It's also possible for that to have a value of h bar, or 2h bar, or negative h bar, or negative 2h bar, etc. But you can't have any value that's in between 0 and h bar. That's just physically impossible. So again, that's something that you can learn more about from studying quantum mechanics, but fundamentally, that comes from the idea that if you start at one place and move 360 degrees around the circle, every physical property has to be the same when you get back to where you started. That's what leads to the quantization of angular momentum. So it's not that complicated of an argument. But we'll just take that as a given, that there is this, oh, and let me, as an aside, just mention that there's a different kind of angular momentum called spin. This is not very important for our class, but I just want to let you know that it does exist. And similarly, for the spin angular momentum, which you could think about as the angular momentum of an object spinning on its axis instead of moving in a big circle, that has allowed values, let's say for an electron, of minus h bar over 2 and h bar over 2, but still the spacing between them is the same spacing of h bar. Okay, so it's a universal feature that the interval between the allowed values of L, for example, let's put L sub x would be equal to h bar, and L sub x is Ix omega x. So the intervals of Lx I can write as the changes in Ix omega x. Here we're talking about the rotations in particular of a diatomic molecule. So I sub x is determined by the structure of the molecule. And so it doesn't change. It's a constant. So if we think about changing the angular momentum, really you're not thinking about changing the shape of the molecule, but rather just changing the speed at which it's rotating. So I could rewrite that delta L sub x is, I can pull out the I sub x part and multiply it times delta omega sub x. And so h bar is Ix delta omega sub x, and so I could rearrange this to delta omega sub x equals h bar over I sub x. So we can see that the spacing between the allowed values of the angular velocity for rotations about a particular axis are inversely proportional to the moment of inertia about that axis. So in particular, that means that the spacings for rotations about the z-axis would be inversely proportional to I sub z, but we argued last time that I sub z is tiny. And so that means that delta omega sub z is huge. So if I were to try to make a plot of the allowed values of omega sub z, there would be 0 is one of those allowed values. The next one up would be some huge distance in omega space above that. So now let's think about the consequences of that for the equipartition theorem. So the equipartition theorem again talks about, in order to have this thermal energy, the spacing between quantum energy levels has to be much less than kBt. So let's think about the spacing between quantum energy levels for rotations about, excuse me, about the z-axis. The kinetic energy of rotations about the z-axis is 1/2 I sub z omega sub z squared. So the spacing between them, the change in the rotational kinetic energy about the z-axis. Again, I sub z and 1/2 are constant, so I can pull those out. So it'd be 1/2 Iz times the spacing of the quantity omega z squared. So if the spacing in omega z is huge, that also means that the spacing in omega z squared is huge. And so this is going to always be greater, much greater than kBt for any temperature that's accessible in the universe. So even if you're inside of a star, the hottest part of a star, you're nowhere near getting to having this quantum spacing comparable to kBt. It's always way bigger than that. So what that means is, if I make this plot where I'm plotting the rotational levels for rotations the energy for rotations about the z-axis. Again, 0 is possible. There is some higher level here, and the highest temperature available in the universe is some tiny, tiny fraction of that. So you never can get out of the ground state for this. The system is always in the ground state. And so it's as if you can't rotate about this axis. So you might as well drop that from considerations of energy. Questions? Okay, so we've made a prediction that there will never be any energy associated with rotations about the z-axis. How can we test that prediction? So how to test these predictions experimentally. One of the main ways you would do it is by measuring the heat capacity. It's been a little while since we've talked about the heat capacity, so I'll remind you of the definition. Capital C is defined to be the derivative of the energy you put into a system with respect to temperature. So I could rewrite this as delta Q over delta T, where delta Q is the energy added to a system. And delta T is the resulting temperature change. So let's think about how you would do this experiment to measure heat capacity, let's say of a gas. You could have a box and you fill it with gas, and then you apply some heat to it in a measured way. So apply a measured amount of heat to it, delta Q, and then you measure the resulting change in temperature, and you take the ratio, and that gives you the heat capacity. So let's back up a little bit and consider a simpler system. So I'm gonna, maybe I'll rewrite the whole energy for a diatomic gas, but then we're gonna simplify it. So diatomic gas, the total energy is 1/2 mvx squared, 1/2 mvy squared, 1/2 mvz squared, plus 1/2 k r minus r naught, that quantity squared, plus 1/2 mu v relative squared, plus 1/2 I x omega x squared, plus 1/2 I y omega y squared. I'm not even going to bother to write the z term because, as we've just talked about, that just never comes into play. So to start with, let's consider a monatomic gas. This will make things a lot simpler for us. Monatomic gas, meaning a gas that doesn't form molecules, but just consists of individual atoms, like helium or argon would be two good examples of that. If we think about the moment of inertia of a monatomic gas, it's tiny no matter what axis you're talking about, because all the mass is in that nucleus of that. And so I sub x and I sub y are also tiny. And so Ix equals Iy equals Iz equals tiny. And so you're always in the ground state for rotations for this monatomic gas. Also, there are no vibrations because there's nothing to vibrate with respect to. So the total energy for a monatomic gas consists only of the translational components. 1/2 mvx squared, 1/2 mvy squared, plus 1/2 mvz squared. So according to the equipartition theorem, each of these is a term that is proportional to a velocity squared. And so on average, so we could write that the average total energy for a single atom would be 1/2 kBt for each of these three terms. So total of 3/2 kBt. So now let's calculate the heat capacity of this. We are going to do our heat capacity experiments at constant volume. We'll talk next time about what happens if we allow the volume to change. But just a little bit of a preview, if I had my gas, let's say, in a container that could expand, then the gas would do work against the walls of the container as it expands, and some of the energy that you added into the system would go into that work. But if we're working at constant volume, then there's no expansion, no work is done by the gas. So that means that all the delta Q added to the system goes into the molecular energies. So I could write that delta Q is equal to delta E of the molecules. And so if I think about the heat capacity of one atom in this case, normally we'd write that as dQ by dt, but because delta Q equals delta E, I could write this as dE by dt. We just showed that the energy is 3/2 kBt. So when I take the derivative of that with respect to temperature, what do I get? You got to unmute, Davey. No. So it might help if I sort of substituted different symbols. Let's say if I said y equals ax, and I asked you what's the derivative of y with respect to x, what would that be? Been a long time for you guys, I guess.
A.
It's just A, exactly. So if we use that same way of thinking, E is 3/2 kBt, 3/2 is just a constant. So what's the derivative of E with respect to T?
Is it 3/2 kb?
Exactly, it's just 3/2 kb. So that's the heat capacity of a single atom. Most of the time when you're doing an experiment, you don't measure the heat capacity of an atom, but often you talk about the heat capacity of 1 mole of a material, which is called the molar heat capacity. I'm going to abbreviate that C sub capital M. And so that would just be the heat capacity of one atom times the number of atoms in a mole, which is Avogadro's number. So that would be 3/2 kb times Avogadro's number. And last time we showed that kb times Avogadro's number, that's just the universal gas constant. So this is a remarkable prediction that no matter what gas you're talking about, if it's a monatomic gas, its heat capacity is 3/2 R, period. That's it. And if you measure this experimentally, the prediction is borne out exactly. So the equipartition theorem really works. Questions? Yes, Ariana?
So we went through that whole process with the Z rotation and determined that because I was really tiny, then the KBT didn't apply. And then when you moved on, you said that all of the I's were tiny, but then
for a monatomic gas.
Okay. So
for a diatomic gas, IX and IY are not that tiny. That's what we're about to talk about. But for a monatomic gas, you just got basically all the mass in this tiny, tiny nucleus. And so the moment of inertia about any axis is really small.
but that wouldn't, but it still satisfies the KB, like the equipartition function with KBT?
No, so in the sense that KBT is much less than the quantum level spacing for any kind of rotation for a monatomic gas. So basically, monatomic gas atoms cannot rotate. Quite surprising.
Okay, so then when we're looking at the E total at the top of the screen, are we not thinking of rotation?
Right.
Then?
So there's no rotations. That's why I wrote it this way. There's no rotations. There's also no vibrations because there's nothing to vibrate with respect to. So there's only translation. Good question. Okay, so now your turn. Let's think about for a diatomic gas. So you already have this in your notes. I'm not going to spend the time to rewrite it right now, but back up here. Here's the total energy of the diatomic gas. I want you to assume a high temperature limit, meaning we're going to assume that KBT is much greater than any of the remaining quantum level spacings except for rotations about Z. What is the heat capacity? What is the molar heat capacity? C sub M. Okay, I'm going to assign you to breakout rooms. 2, 3. Well, there's a lot of you, which is fine. Before I assign you to breakout rooms, is there any questions about the concept test we're trying to address? Okay, so you can use the same techniques we were just using for the monatomic ones, but now you have this longer expression for the total energy. Okay. All right, you can go ahead and join your room. Okay. Scott, can you get us started, please?
Sure. So we were looking at the like similarities between the energy total formulas for diatomic gas versus the monatomic gas, and immediately saw that the translational terms would again be each correspond to a 1/2 kBt for average total energy. And then we also found that each of the rest of the terms was either velocity squared or position squared, and that each of them therefore accounted for another 1/2 kBt term.
Okay, give me a second to catch up here. So I'm just writing again the total energy for a diatomic molecule. We've got the translational terms, which, as Scott said, each of those is proportional to a velocity squared, so that each of them gets a 1/2 kBt. For the vibrations, this relative velocity, that's independent of the velocity of the center of mass. So that gives us another 1/2 kBt for that term. For the potential energy associated with the vibration, this relative motion, r minus r naught, that's independent of the motion of the center of mass. So that's a position squared that counts for the equipartition theorem. So that's another 1/2 kBt. And then finally, we've got the two rotational kinetic energies. And recall, as we said last time, that rotational velocity, angular velocity, counts as a velocity. So each of these gives us a 1/2 kBt. Amanda, can you pick it up from there? Amanda's having a little trouble with her internet today. So Davey, how about you?
Sure. So since we deduced that each of those terms is 1/2 kBt, it totals up to 7/2 kBt as the energy total. And looking back at the equation that we used to determine the heat capacity of a monoatomic gas, that would be the derivative of the total energy with respect to the temperature. And so in this case, that would be 7.5 kB.
Good. All right, somebody else finish it out for us. What does that mean for the molar heat capacity?
Would that mean the molar heat capacity is 7/2 kBs Avogadro's?
Exactly. So the molar heat capacity would be the heat capacity of one atom times Avogadro's number, which, as Marissa said, would be 7/2 kBNA, and kBNA is R. So we've made another bold prediction that no matter what diatomic molecule you're talking about, whether it's hydrogen chloride, H2, O2, N2, anything, at high temperatures, its molar heat capacity is 7/2 R. And again, when you make these measurements, it's very well borne out by experiments. Okay, so now let's add a little bit more reality. The energy spacing for rotations about the X or the Y axis, it does depend on the exact molecule that you're talking about, but that's typically about equal to kBt when T equals 200 Kelvin. The vibrations are also quantized. So again, this is something that you will learn about if you take PChem or introductory quantum mechanics, but the delta E for vibrations turns out to be h bar omega, where omega here is the angular frequency of vibrations. So we use the same symbol for angular frequency and angular velocity. And that's because, as we maybe will talk about next time, there is a deep mathematical connection between rotational motion and vibrational motion. But for our purposes, we can just say that omega, the angular frequency of vibration, is 2 pi over the period of vibration, which is 2 pi times what you might think of as the normal frequency of vibration. That is, how many times per second do the atoms vibrate back and forth. So vibrations are quantized like rotations, and that interval of energy, the quantization spacing for energy of vibrations, is about equal to kBt when the temperature is about equal to 2000 Kelvin. So now we're going to make a graph. So on this graph, we're going to graph the molar heat capacity of a gas as a function of temperature, of a diatomic gas, I should say. What we already showed is that, and this temperature, we're going to use a kind of log scale. So here's 2000 Kelvin and 200 Kelvin. What we already showed is that at very high temperatures, the molar heat capacity is 7/2 R. I want you to roughly fill in the rest of this graph. So I'm going to give you a chance, because I just realized that when we go to breakout rooms, you can't see my screen anymore. Give me a nod when you're ready to go to the breakout room. Okay, I think we're all back. Sydney, can you get us started, please?
So between 200 Kelvin and 2000 Kelvin.
So if the temperature is less than 2000 but greater than 200.
KBT is larger than delta E rotational on the X and Y axis, but smaller than delta E vibrational.
Good.
So you lose all the vibrational energy terms because.
So I'm just going to rewrite the energy for a single molecule. We've got these three terms for translation, the two terms for vibration, 1/2 mv relative, sorry, this is mu v relative squared, and the two terms for rotations, I y omega y squared. And what Sydney just said is that you're going to lose these two terms. The technical phrase for that is that these quote unquote freeze out. These terms freeze out when T is less than 2000 Kelvin, meaning you're no longer in the regime where you have enough thermal energy to be promoted ever out of that ground state to the first excited state. So it's as if, it's not as if, at that point the molecule is no longer able to vibrate. It's always stuck in the ground state of the vibrational energy. And so in that state, Sydney, what's the total energy becomes?
It would be 5/2 kV T.
So E total, then we now have 1, 2, 3, 4, 5 times 1/2 kBt. So it's equal to 5/2 kBt. And what does that mean about the heat capacity?
The heat capacity, molar heat capacity would be 5/2 R.
Right. So basically what Sydney did was take a little shortcut and realize you just, to calculate the molar heat capacity, you just count up the number of terms that have not been frozen out. And so and multiply that times R over 2. So it's 5/2 R. Or if we wanted to write it out in a little bit more detail, we could say that the heat capacity of one molecule is the derivative of the energy of one molecule with respect to temperature. And since the energy is 5/2 kBt, when we take the derivative, that's just 5/2 kB. And the molar heat capacity is the heat capacity of one molecule times Avogadro's number. So that's 5/2 kB times Na, which is 5/2 R. Yes, Allison?
What does it mean for a term to freeze out?
It just means, this is a good question. This just means that kBt is significantly less than the energy spacing between them. So when that's the case, so let's say we're talking about vibrational levels. Where am I going to draw this? Down here. Here's the ground state for vibrations. And here I'm plotting the energy associated with vibrations. Here's the first excited state. And when the kBt is like this, all of the molecules will be in this ground state. So they can't have any energy other than that associated with the ground state. And so there's no contribution to the heat capacity from that mode. Does that address your question, Allison? I'm not sure if she's frozen or just deep in thought. So if kBt is much less than delta E, can only exist in the ground state. There's not enough thermal energy available to be promoted from the ground state up to the first excited state. Okay, so let's finish our graph then. So what we just showed is that in this regime between 200 and 2000, the heat capacity is going to be about like so, where this is 5 halves R. And kind of between here and 2000, it kind of mushes. We're not going to worry about the details, but it sort of slides somehow from 5 halves to 7 halves R. Okay, I forget who I was talking to earlier. So who would like to pick up at what happens when we get below 200 Kelvin? Phoebe?
So when you get below 200 Kelvin, the rotational energy terms freeze out.
Exactly. So these are going to freeze out for T less than 200 Kelvin. Go ahead.
So your energy total is equal to 3 halves kBT in that situation. So the molar heat capacity is equal to 3 halves R when the temperature is less than 200 Kelvin.
So it's going to go down to 3 halves R, and again, it's going to kind of mush in between here. So now we have a powerful prediction for how the heat capacity varies in temperature with respect to temperature. And if you measure this, this is what you get. The transition temperatures do depend on the details of what molecule you're talking about, but the levels at each plateau are universal for all diatomic molecules. So you might ask, why do we care about these vibrational levels when the temperature is so high? You know, I don't care about temperatures of 2000 Kelvin. And there are two reasons. So one is that there are places where the temperature might reach 2000 Kelvin, like in a flame. Another is for infrared spectroscopy. So let's have a short aside for infrared spectroscopy. Recall, I told you I didn't prove this, but that the difference in vibrational energy levels is h bar times omega, where omega is 2 pi times the frequency of vibration. And so if we plot the vibrational energy levels, I'm going to make that plot again here. Here's the ground state. So I'm just plotting energy. Here's the first excited state, first vibrational excited state. You cannot be promoted at room temperature, which is about 300 Kelvin, from the ground state up to the first excited state. But if you shine light of the right frequency on this, you can absorb a photon. So absorb an infrared photon. So a photon is like a particle of light, and that can give you just the right amount of energy to jump from the ground state up to the first excited state. The energy of a photon is also equal to h bar omega, where this is the angular frequency of vibration of the photon. So the photon, as you're going to learn next semester, consists of wiggling, vibrating electric and magnetic fields. And so if those electric and magnetic fields are vibrating at the same frequency at which the molecule vibrates, then they can inject energy into that vibration. Maybe you can see that qualitatively because you will learn that light consists of these electric and magnetic fields. So if the electric field is vibrating left and right, it's pushing the electrons left and right, and that's what causes this vibration and can increase its energy. So if you plot the spectrum of the amount of light that's absorbed as a function of its angular frequency, you will find these peaks that correspond to promoting from the ground state up to the first vibrational excited level, or from the ground state up to the second vibrational excited level. So you can use these to measure the omega, the angular frequency associated with that vibration, and that in turn gives you information about the molecule, about how it's the atoms that make it up and how those atoms are distributed in space. Okay, let's do one more example using the equipartition theorem, which is the heat capacity of solids. So we're going to model a solid. Each atom in the solid is in an equilibrium position. That's the definition of a solid. So that means that it's interacting with the atoms around it by forces that we can model as springs. Because as we talked about, anything that's in equilibrium, the total force on it is like a spring force, at least if you're near equilibrium. There would also be springs leading to atoms that are above the plane of this page and below. So there are interactions in 3 dimensions. So for each dimension, the atom has energy associated with vibration. So the total energy, let's say for this central atom, for vibrations in the x direction would be 1/2 mvx squared plus 1/2 k sub x squared. So the kinetic energy of vibration and potential energy of vibration. And that applies also for the y and the z directions, because all 3 directions are the same. Okay, that's the setup. The question is, for, again, temperature much greater than whatever the quantum energy spacing is for vibrations in this system, what is the molar heat capacity? Any questions before I put you in your breakout rooms to talk about this? Okay. So you can join your rooms now. Okay. Let's see, Hannah, can you walk us through it, please?
Yes. So when you're looking at the total energy in either the X or the Y or the Z dimension, you will get 1/2 kBT plus 1/2 kBT. So if you do that.
Okay, let me just pause you for a second. So what Hannah is talking about is this is a velocity squared. This is a position squared. So each of them has 1/2 kBT on average of thermal energy. Go ahead.
So if you do that for each dimension, you'll end up getting a total energy of 3 kBT.
So there's total of 6/2 kBT, which is equal to 3 kBT for all 3 dimensions. Good.
And then you'll get Cm to equal to 3R.
So Cm equals 3R. So again, this is a very bold prediction we're making. No matter what the solid is, if you're at high temperature, its heat capacity is 3R. And again, it is borne out pretty well by experiments. Not as perfect a match as it is for the gases, but it's pretty darn good. It will not surprise you at this point that as you lower the temperature of a solid, the heat capacity starts to drop below this limit because you're starting to get some of the vibrations freezing out. And next time we'll talk a little bit more about that. Okay, that's it for today. Thank you.